In this chapter, we will be using calculus as a tool in curve sketching. In this video, we'll be sketching the curve of 2 divided by x squared minus 4.
All right, here's another one. We're going to look at f of x equals 2 over x squared minus 4. And we're going to graph this function right here. And this one here is actually should be a little bit easier because we're going back and looking at a function that you've probably seen from another course. It's just that now we're going to use calculus to kind of fill in some of the gaps that you might have had earlier on. So first of all, let's take a look at the domain. And notice that this function right here, when you factor that denominator, you're going to get that x cannot equal positive or negative 2. Now let's look at the intercepts. Okay, so let's look at the y-intercept first. So this is just going to be f at 0. So 2 over 0 squared minus 4. Okay, that's just going to be negative 1/2. If we want to get the x-intercepts here, okay, that is going to be set the function equal to 0. So 2 over x squared minus 4 is equal to 0. Now, but bear in mind that a rational expression, the denominator has no impact on whether that rational expression goes to 0. So it turns out here that there is no x-intercept. Okay, whoops, no x-intercept. Good. Let's take a look at symmetry. So if I plug in negative x into this expression, because the x is being squared in the denominator, that negative is going to disappear. And so this is simply going to be 2 over x squared minus 4, which is actually the original expression. So the negative completely disappears. Therefore, this is even. So it's symmetric, okay, about x equals 0. Okay, that is symmetric about the y-axis. It's got that bilateral symmetry. And not that we're going to use that to help us graph this, but we will see it pop out later. In fact, if our graph doesn't show that kind of symmetry, we'll know that we've done something wrong. All right, number 4, asymptotes. Okay. Now this one has got asymptotes. So we know that this one's got vertical asymptotes at x is equal to positive and negative 2. So what we're going to do right now is we're going to take a look and we're going to investigate how the graph behaves on either side of those asymptotes. So let's take a look really quickly at the limit as x approaches negative 2 from the left of f of x. Actually, you know what? I'm going to, instead of writing f of x, I'm actually going to write this out. I'm going to write it out in factored form. So this will be x minus 2, x plus 2. Okay. As I approach negative 2 from the left, this bit right here, this factor, x minus 2, is going to approach negative 4. And I have no problems with negative 4. Okay, as a value, that's not causing me any stress whatsoever. So what? It's approaching negative 4, no big deal. This one right here, though, is going to approach 0. But the question is how? Does it approach 0 from the negative side or from the positive side? So when you take a look at the number line here, okay, if this is 0, and here's our negative 2. If we approach negative 2 from the left and add 2 to it, then the result is that we're approaching 0 from the left. The reason that's significant is because to the left of 0, they're all negative numbers. So this is going to be approaching 0, but from the negative side. Okay, this was also negative. So 2 divided by a negative times a negative, the answer here is this is going up to positive infinity. If we take the limit as x approaches negative 2 from the right of 2 over x minus 2, x plus 2, once again, this x minus 2 is only approaching negative 4. So what? It's what's happening over here. And this time, as you approach negative 2 from the right, when I add 2 to that, that's going to push me over into the positive side. So as a result, this term is negative, but this term is always positive. That's going to negative infinity. Now let's take a look at what happens when you approach positive 2 from the left of 2 over x minus 2, x plus 2. Well, this time the roles are reversed. X plus 2 is approaching 4. Okay, again, not a big deal. But x minus 2 is going to be approaching 0. And if you approach positive 2 from the left and then subtract 2 from it, that's going to put you to the negative side of 0. So as a result, this is going to be negative. This is going to be positive. I'm approaching 4, so no big deal. So as a result, this is going to drop down to negative infinity. Because remember, in all these cases here, I'm approaching 0, which means the denominator is getting really, really small, so the whole thing is going to get really, really large, but in this case in a negative direction. Now I'm going to approach 2 from the right. And once again, x plus 2 doesn't have a problem with that. It's just approaching 4. But x minus 2, as I approach 2 from the right, when I subtract 2, I'm still on the positive side. So this will be positive 4, this will be positive side of 0. So altogether, that's going to give me positive infinity. Awesome. So not only do I now know what the vertical asymptotes are, I know exactly how it's behaving on either side of those asymptotes. The only other thing I need to notice here is that, notice that the degree of the denominator is larger than the degree of the numerator. So I know that this also has a horizontal asymptote at y is equal to 0. And we'll see how that plays out later on. Okay, now let's take a quick look at intervals of increase and decrease. And so what I'm going to do with our function here, just because I'm a little on the lazy side, is I'm going to write this in this form. I'm going to bring up the denominator, just take it to the negative 1, so that when I take the derivative here, this will be negative 2 x squared minus 4 to the negative 2 multiplied by 2x. Okay, I'm just going to use the chain rule in this case. Okay, and so let's rewrite that just in a way that looks a little bit better. That's going to be negative 4x over x squared minus 4 squared. I am interested in where this function is is 0 or undefined in the domain of the function, because those are my critical values here. Now, this is undefined. Okay, this is going to be undefined at positive and negative 2. However, the original function was also undefined there, so those don't count as critical numbers. Okay, so not critical numbers here. But the whole thing is equal to 0 when x is equal to 0. So that will be a critical number here. So this is the only one that qualifies as a possible max or min. These ones right here are significant because the intervals of increase and decrease can change on either side of plus or minus 2. But that's because we're looking at asymptotes. And behavior can change dramatically on either side of an asymptote. Now, let's just take a quick look at the function here. So here's negative 2, here's 0, here's positive 2. Now, here's the fun thing about this. Once we've got the asymptotes here, I can actually kind of sneak around this a little bit. I can kind of use the asymptotes to tell me whether I'm doing this correct. Just watch. So here, notice that the denominator will always be positive. But the numerator will only be positive when x is negative. Okay? So what that means here is that it's going to be positive here, negative here, negative here. Okay? Because as soon as the x value becomes positive, then the numerator becomes negative, and the denominator is always positive. So the denominator is really not having an impact on this. Now, take a look at what's going on here. To the left of negative 2, it seems to be going up, and to the right, it seems to be going down. So now, just watch this. If here's negative 2, to the left it's going up, to the right, now notice what this means. This means it's increasing, which means it must have started low. So there we go. That makes perfect sense. Increasing, increasing. Going up, starting from low and coming up. So yeah, that is perfectly in line with what I was expecting from my asymptotes here. So that tells me I'm on the right track here. Now, notice that I go from increasing to decreasing here, so this tells me that I've got this max here. Oh, sorry, I'm jumping the gun. We should identify the intervals of increasing and decreasing. So the first derivative is going to be positive from negative infinity to negative 2 union negative 2 to 0, which means the function is increasing from negative infinity to negative 2, and I don't include the negative 2 this time because it's an asymptote, union negative 2 out to 0, and this time I do include it because this 0 is part of the original function. Okay, it's not an asymptote. The first derivative is negative on the interval 0 to 2, union 2 to infinity, which means the function is decreasing from 0, including 0, out to 2, but not including 2, not including the asymptote, out to infinity. So as a result, over here, questions with part 6, I can talk about maxes and mins. I know that I've got a max at the spot where x is equal to 0, and we've already figured out where that is because that actually matches up with my intercept. So it's going to be at 0, negative 1/2. Love it when that happens. Just makes things easy. Now, and actually that is consistent with the symmetry that we've got as well here. We know that's symmetric about the y-axis here, so it actually kind of makes sense that my max would be right on the y-axis there because I've only got the 1. All right, 7. Now we're going to look at concavity, which means we're taking that derivative again. So let's use the quotient rule this time. It's always good to practice the quotient rule. So the derivative of the numerator will be negative 4 multiplied by the denominator minus the numerator multiplied by the derivative of the denominator, which will be 2x squared minus 4 multiplied by 2x. So that's kind of a beast, that guy right there. And then this will be over the denominator squared. Got to remember to square that so it becomes to the 4th. But now we can factor this. We can simplify it a little bit. I will take out a negative 4 and then x squared minus 4 just to the 1. So that will leave me with x squared minus 4 from the first term here. I took out one of the negatives, so I'm still left with another negative, minus, I took out the 4, I'm going to be left with an x and 2 factors of 2, so 4x squared. All over x squared minus 4 to the 4th. Well, one of those factors will cancel with one of those, so it'll be cubed in the bottom here. This will be negative 4, what have I got here? Negative 3x squared minus 4 all over x squared minus 4 cubed. And then I can take out the negative, and so we're left with 3x squared plus 4 over x squared minus 4 cubed. Okay, so now we are looking for where this is 0 or where it's undefined. It's going to be undefined at 2 and negative 2 again. Okay, that's because the original function was undefined there. And that it will never happen that the original function is undefined and then one of your derivatives along the way suddenly becomes defined there. If it was undefined at the beginning, it'll be undefined all the way through. So it's going to be undefined at plus or minus 2. So then the question is, where does it go to 0? Actually, interestingly enough, just take a look at that numerator there. It never will go to 0. There is no number that you can square, multiply by 3 and add 4 and get 0. And the reason for that is every time you square a number, you get a positive result. Okay? If we were going to multiply by 3 and add 4, then as soon as we multiplied by 3 here, we should be getting a negative 4 as a result, and you simply can't do that. So this is the only spot where that occurs. So negative 2, positive 2. Sorry. So take a look here. We know that the numerator is always going to be positive. If you pick a number less than negative 2, square it and subtract 4, you're going to get a number that is bigger than 0 cubed, so it's going to be positive. As soon as you pick a number between negative 2 and 2, and square it and subtract 4, that will be negative, and the cube will keep that negative on there. So it's going to be concave down in between, and then by that kind of symmetric argument, it'll be positive over there. So our second derivative is positive from negative infinity to negative 2, union 2 out to infinity, which means this thing is going to be concave up, and in this case it will be exactly the same interval. That's because those are asymptotes and I can't include those. This will be, second derivative will be negative from negative 2 to 2, which means this will be concave down on, again, exactly the same interval. Which means for us, for 8 points of inflection and cusps, well, there are none. Okay? Because where the concavity changes, those aren't points, those are asymptotes. Okay, so good. So now we can sketch this. And actually, there's not a whole lot going on here that'll kind of surprise anybody. Here's my negative 2, here's my 2. And in fact, I'm not actually going to run through the whole procedure that I would normally do for this because actually this graph is really straightforward. I know that it's also got a y-intercept here at 0, negative 1/2. And it's also got an asymptote here along the x-axis. Now, over here, it was supposed to be increasing and concave up. If I've got an asymptote here and an asymptote here, and it's going up to infinity on the left, it's gotta look something like this. Here, this was increasing, this was concave down. In fact, this little interval in between both those asymptotes is concave down. And I knew that this was a maximum here, so it's gotta look something like this. And then over here, this was it was decreasing in this little interval. Here it's decreasing, and again, concave ups with those two asymptotes, it's gotta look something like that. Okay, and you would have known that before in an earlier math course. What would have been missing is information about how it behaves in between. We knew it would look like this, but we just didn't know where it would go. Anyway, I hope that makes sense.